Welcome to DVCon U.S. 2022. Hi, my name is Harry Foster, and I'm Chief Scientist Verification at Siemens EDA. And welcome to the sponsor tutorial titled, The Best Verification Strategy You Never Heard of. Now, I'm thrilled to have the opportunity to kick off this tutorial since it's a topic dear to my heart. Now, I have divided my introduction into three parts: the crisis, the problem, and the prescription. Let me begin my discussion on the crisis by stepping back in time to 1997, when Semitech set off an alarm in the industry by what they called the design productivity gap. Now, the essential idea was that we could manufacture more transistors than we had time to actually use in terms of design. In other words, manufacturing productivity gains increased at a 40% CAGR, while design productivity gains increased at only a 20% CAGR. Now, it turns out the design productivity gap never really happened. There are two main reasons for this. EDA improvements increase productivity, but probably more importantly was the emergence of a design reuse methodology or various methodologies, and the emergence of design IP economy along with an ecosystem. Since this time, a more ominous productivity gap has emerged. And we refer to this as a verification productivity gap. Now, keep in mind that design complexity grows at a Moore's law rate, yet verification complexity grows at a double exponential rate with respect to Moore's law. And although verification reuse and verification IP is a critical ingredient in addressing today's growing verification complexity, it will not be enough to solve the verification gap. We can quantify the growing verification productivity gap a couple ways. For example, on this slide, I'm showing the increased verification and validation costs by node feature size. Another way to quantify the cost is to look at the trends in terms of mean peak number of engineers on ASIC projects. Since 2007, design engineers working on a project have increased by 32%. Yes, verification engineers has increased by an alarming 143%. Yet, with this increase in verification engineers, only 1/3 of ASIC projects are able to achieve first silicon success. But it's not just ASIC projects. We find today that 83% of FPGA design projects have non-trivial bug escapes into production. Many of these bugs can be extremely costly to fix in the field. On top of that, we find that 2/3 of all projects are behind schedule. Clearly, we have a verification crisis. Let's now focus on the problem. First of all, I want to go back to the 1990s again, when we began seeing the emergence of verification teams. Or the separation of design and verification. This was done for two reasons. First, to ensure an independent interpretation of the specification that would assist in flushing out design errors. And second, increased complexity of verification environments required unique engineering skills. This has led to an extreme situation in some cases where design is thrown over the wall, and more importantly, a fallacy that quality can be verified into a project, which is just not true. In fact, to make this point, I want to reference Dr. W. Edward Deming. He was often referred to as the father of statistical process control. Deming was invited into Japan after World War II and totally revolutionized their manufacturing capabilities to lead the world in terms of quality products. In his landmark book in 1985, titled Out of the Crisis, Deming made the point that quality cannot be inspected into a product. It must be built into it. Deming was famous for conducting exercises in his quality management training courses. To illustrate his point about quality, he filled 2 wooden boxes with white beads and then added a handful of red beads to represent bugs. He then divided his class into 2 groups, and he gave each group a wooden box and with a paddle to remove the red beads. His plan was to reward the group that removed the greatest number of red beads and penalize the other one. After the exercise, each group shared their experiences of basically focused on techniques they used to remove the red beads. Deming, however, told the class that they totally missed the point. It didn't matter if you reward or punish a group in terms of how effectively you remove the beads. The result was the same because the red beads remained. His key takeaway was that finding an optimal process to remove the red beads was not the solution. The real solution was not to put the red beads in the wooden box in the first place. Now, this wisdom is applicable to IC design today. An industry analysis of IC respin root causes has revealed cases where not only complex corner case bugs are escaping into production, but also trivial bugs. For example, even after billions of cycles of coverage-driven, constrained random simulation combined with directed testing, one high-end server project in the analysis experienced an out-of-range indexing error that resulted in data corruption. Now, this simple yet costly respin could have been avoided if the design engineer simply ran lint on the RTL code prior to checking it in. Without question, this outlier is an extreme case. Yet even if this simple RTL bug was caught prior to tape-out, the cost of triaging, debugging, and redesigning followed by additional verification is significantly higher when caught later in the development lifecycle. To help understand the cost impact on a project, this slide, we quantify the cost multipliers associated with finding and fixing bugs at various stages in the development lifecycle. In early stages on the project, the cost is predominantly due to labor and other resource expenses. Notice that bugs found at the IP verification stage is 8 times more costly than it found at the coding stage. This is due to the increase in resources required to identify and triage bugs after coding. Obviously, the cost multiplier increases significantly during the post-silicon stage, where expenses include not only labor, but also expenses associated with building hardware, such as silicon and validation boards and prototypes. Now that we've discussed the crisis and understand the problem, let's shift gears and focus on the prescription. Design bugs are introduced throughout all phases of the development lifecycle, including the architectural, design, synthesis, integration, and physical design phases. To reduce the cost of finding and fixing bugs, methodologies that promote testing early and often have recently emerged, such as shifting the verification phase to earlier in development lifecycle combined with continuous integration. Yet today's crisis will not be solved solely through improvements in verification methodologies and techniques. A solution requires a holistic and philosophical change in the design process with a foundation based on bug prevention. Now, I refer to this fundamental change as design using intent-focused insight, or design plus intent. Ultimately, the goal is to reduce bug density at later stages in development, which have higher cost factors to fix. Now, in the tutorial today, we're going to go through details on the 3 pillars of a design plus intent methodology. And those pillars are the produce, that's the produce the correct intent by construction, the prove intent is met, and protect intent throughout the design lifecycle. And again, this is a design plus intent methodology. A development lifecycle that incorporates design plus intent does not make verification any less important than it has been. In fact, the goal of design plus intent process is to improve verification efficiency by decreasing bug density, which impacts downstream processes and consequently reduces cost. While a design plus intent bug prevention strategy encompasses all aspects of IC design, there are design solutions that exist today with the principal focus on improving RTL quality, such as static analysis. I want to focus on one of the pillars of the design plus intent methodology, and that's the produce pillar, and specifically how high-level languages and high-level synthesis plays into this. One question many engineers ask me is if certain RTL languages are more susceptible to bugs than others. Now, the answer is no. In fact, this has been observed across many software projects for years, where the specific choice of language was irrelevant in terms of the number of bugs. In fact, this has been quantified across multiple software projects in terms of number of bugs per 1,000 lines of code. On average, software projects consistently observe between 15 to 50 bugs per 1,000 lines of code, depending on the complexity of the code. And this software bug density pattern is also true for hardware projects using RTL. Now, by leveraging high-level languages such as C or C++, we reduce the number of lines of code that are required to describe the design. For example, in some cases, you might have 100 lines of a high-level language is equivalent to 1,000 lines of RTL. With this reduction in the number of lines of code, we should also expect a 10x reduction in the average number of bugs. For example, we would expect 1 to 5 bugs for the high-level language design versus 15 to 50 bugs for the equivalent RTL design. Now, an important point is not only are we reducing the bug density by moving to a high-level language, but we're also speeding up simulation through abstraction. Yet not all design blocks lend themselves to high-level synthesis. Therefore, another key part of the produce pillar is an HDL design environment that integrates deep analysis capabilities into the creation process. These can quickly assess new and used code quality to prevent bugs during development. Okay, the final part of our tutorial today focuses on what I call beyond verification, and this is very important in the SoC lifecycle. Here we're talking about hardware validation and firmware enablement, and software enablement and system validation. This is used in emulation and prototyping. On a final note, if you found anything I discussed today interesting, I have a detailed white paper on the subject which I titled Out of the Verification Crisis, Improving RTL Quality. So I hope you enjoy our tutorial today.
Thank you, Harry, for getting us started and for describing the 3 pillars of a design plus intent methodology as a prescription for addressing the productivity gaps. Hello, everyone. My name is David Aerne, a verification technologist with Siemens EDA. And in this section, we'll go into detail on how to address the productivity gaps, focusing on produce, the first of Harry's 3 pillars. In particular, we'll look at high-level synthesis, or HLS, and how it provides us with the ability to design at a higher level of abstraction. This not only allows us to quickly get to a working design, yet also allows us to rapidly iterate via architectural exploration over various implementations before committing to RTL. And as HLS incorporates our target technology node, the result is RTL which meets not only timing requirements, yet also our performance, power, and area goals. We'll also take a closer look at high-level verification, or HLV, performed using known and trusted techniques, that is, the same ones traditionally used for RTL verification, though with the speedup obtained due to the DUT abstraction level, and how thorough and rigorous HLV leads to efficient and predictable post-HLS RTL verification sign-off. Let's jump in. Starting with HLS, now it provides for a rapid path from algorithm to hardware, that is, RTL, and calling out metrics or results typically seen in projects which adopt HLS. Coding in HLS results in 5 to 10x fewer lines of code when compared to RTL. And the higher level of abstraction provides for faster simulations, typically between 30 to 1,000x faster. We can quickly evaluate various implementations and perform architectural explorations to quickly find a solution which results in optimal power, performance, and area. And as a former RTL designer, I cringe a bit knowing how HLS facilitates late changing specifications, yet it is the case. More relevant, moving to new target technology nodes is easy, say as blocks get reused in next-gen products, or even to facilitate prototyping the same design on an FPGA prior to mass production via an ASIC. Before going into too much detail, a bit of HLS 101. At its simplest, HLS synthesizes untimed C++ and our clock system C to RTL. And sure, system-on-a-chip design is amazingly complex, with one challenge being the timely creation of optimal handcrafted RTL. We lack the ability to discern functionality and PPA trade-offs until late in the game. Does our schedule include time to iterate through this long loop? Alternatively, coding in HLS results in correct by construction RTL. Well, what does this look like? For starters, regardless of coding in either function-based or class-based C++, or SC module or class-based system C, pointing out that the functions and methods in our HLS design source become Verilog modules or VHDL entities within the post-HLS RTL, with the function arguments transformed into ports. As a demonstration vehicle, we will walk through the high-level design and verification of a digital pre-distortion block, a common and important component in communications and wireless markets, such as the 5G segment. The purpose of the DPD block is to compensate for nonlinearity common in power amplifiers. Thus, when the two are used in conjunction, the result is a power-efficient output having a linear response. Perhaps simple in concept, yet the required solution is quite complex in that it needs to incorporate a feedback loop to compensate for varying operating conditions. And as I'm driving an antenna, it handles samples on a continual basis, yet will need a frame-based approach for the training feedback loop, with obvious trade-offs regarding power, performance, and area. We can't have the solution consume more power than the ideal, yet expensive, power amplifier. One additional slide providing yet more detail on the design and the test bench, again both at the C++ level of abstraction. We will break the design into a handful of building blocks, each which will be synthesized standalone via HLS. Then, still via HLS, the blocks will be assembled into our design top. This approach is what's referred to as a bottom-up approach, with assembly of the DUT done from lower-level building blocks. Looking at the design flow and how we can quickly simulate real hardware behavior in our high-level language model. The design of the DPD, as with many communication blocks, began with the development done by an algorithmic team using floating point models. Thus, part of the job of the designer, regardless of if using HLS or not, is to quantize a floating point model into a more area and power efficient fixed point implementation. When this is done using HLS, we have the ability to plug the quantized HLS model back into the same environment, thus ensuring it meets performance requirements. And as this environment typically operates at a higher level of abstraction, it runs quick. Thus, we can use the same environment with the speed advantage to quantify our HLS model all prior to RTL. As Horizon Robotics stated, the advantage here is the ability to compare a C reference model with HLS C hardware model. As briefly mentioned in the previous slide, we will, as with RTL design, want to use bit-accurate data types in our HLS design. Remember, we're modeling actual hardware here. Two choices come to mind, the AC data types and the System C library, both of which are in the public domain and available for download as shown. Of the two, HLS designers generally prefer the AC types over the System C types, even for the System C HLS. And that's simply because the AC types simulate quantifiably faster, again, even for System C HLS designs. As required, data types will need to include the necessary flags to specify rounding and saturation modes. For example, only enabling saturation for the final assignment from a multiply-accumulate operation. And in our first screenshot from the DPD design source, we see a few of the type defs used in the design, in particular an AC complex of an AC fixed type for the real and imaginary components, with the desired rounding and saturation attributes. And again, as with traditional RTL design, HLS designs also draw upon pre-established libraries of intellectual property, or IP. Only now the IP, like the design, are also written in an HLS-ready high-level language. Two libraries from which components are drawn from in the design of our DPD are as shown, namely the AC Math and AC DSP. These two, along with an additional one containing machine learning blocks, are all in the public domain and available on hlslibs.org. As with any IP, we expect and need to be able to customize instances of it within our design. Furthermore, it should automatically support various data types and also have various implementations, allowing the designer to perform PPA trade-offs. For example, choosing a piecewise versus a lookup table versus a Cordic implementation. And in the screenshot, we see a code snippet from the DPD design, highlighting an instance of the AC square root block, which operates on our fixed point data, and note we have picked the area-efficient piecewise linear implementation. Assume at this stage we are designing the leaf blocks for the DPD, and let's see how HLS makes meeting our power performance area goals achievable. The HLS process involves reading of the design and also knowledge of the target technology. The next step is applying the user-defined constraints or directives which define and control the synthesis process. For example, performing loop unrolling and pipelining based upon the designer's input to add parallelism and provide necessary throughput as implementation trade-offs are explored. Not surprising that designing an HLS requires a similar skill set to that for RTL designers. Next, scheduling automatically closes timing by inserting pipeline registers and any related or necessary control logic based on the target technology and the specified clock frequency. And finally, designers don't need to worry about resource or register sharing, since HLS automatically shares based on the design constraints, providing for an area-efficient solution. Up to this point, we've been focusing on leaf blocks, and now we'll turn our attention to creating our multi-block DPD top. Our DPD design, as with many designs, requires multiple concurrent processes to meet the desired performance goals, and HLS builds parallel concurrent processes from our C++ classes. This single-threaded design description is not just easy to design with, yet makes for straightforward debug. As we assemble leaf blocks to build our DPD top, we'll use channels to connect the leaf blocks and thus build our DPD top in a bottom-up design approach. Highlighted here are some of the channels within our DPD design, and noting how HLS automatically handles synchronization between the blocks, namely replacing the channels with FIFOs in the post-HLS RTL. At this point, we've completed the design of our DPD, consisting of multiple leaf blocks stitched together, yet all done via HLS. And thus, this concludes the section on HLS design. We'll now move on to high-level verification, or HLV. Kicking off our HLV section, where we begin to straddle between the produce and prove pillars, we'll be applying known and trusted RTL verification techniques, only here at the HLS level of abstraction. Starting with C Design Checker for static and formal analysis of HLS design source to quickly and easily find coding bugs prior to synthesis and even prior to dynamic simulation. The motivation here is it's possible to write your pre-HLS source in such a way as to be ambiguous when it comes to describing hardware. Ambiguities that could lead to mismatches between the behavior of the HLS model and the post-HLS RTL. And it's not only inefficient to debug these in RTL simulation, yet also too late in the verification cycle. We need various modes of checks, starting with the basic quality of results, or QOR mode. This is a set of informational checks, which look for quality of result issues, such as suboptimal use of a divide operator, or when an array size is a non-power of 2. These aren't design errors per se, just rather want to make sure that this was the designer's intent. There are also a number of static lint type checks, as well as a number of deep formal base checks. And examples of the formal checks are out-of-bounds array reads and writes, ABRs and ABWs, as well as uninitialized memory reads, or UMRs, any of which may result in mismatches between your pre-HLS design behavior and the resulting RTL. Thus, let's get them identified and resolved early on in the HLS design process. Here we show some results of running Design Checker against an early version of our DPD design. In particular, we're focusing on the results of running the 2 of the predefined modes, simulation mismatch mode, as well as the QOR checks. The simulation mismatch results are shown in the top screenshot, where in this situation we're reporting on an uninitialized memory read, or UMR. This is a scenario where the C++ sim may always return a 0 for an uninitialized memory read, yet the resulting RTL will likely show an X during simulation. Best to identify and address this upfront. The other screenshot shows QR findings. These typically show up as warnings or infos instead of error, again warning the user where their coding style could result in less than an optimal result. All of the Catapult Design Checker results can be analyzed via text reports or from within the Catapult GUI. If you use the GUI, each finding is cross-linked to the design source for easier reference and debug. Individual findings can be controlled from a waiver file in order to reduce the output from subsequent runs. Alternatively, you can specify waivers within the pre-HLS source itself in the form of pragmas. Furthermore, since it's a formal-based tool, some constraints may be necessary to guide those formal checks along the correct path, and these constraints also come in the form of pragma statements in the code, specifically assume pragmas. In summary, Catapult Design Checker enables you to produce cleaner HLS design source without need to push the design through synthesis or even simulation, ultimately resulting in less debug of your post-HLS RTL. We now move on to dynamic verification with a look at deploying assertions and cover properties within the HLS design source itself. This is typically done by the designer, just as they might do with handwritten RTL. For example, if the designer wants to ensure that a particular illegal condition never occurs, or if there's a specific mode of operation that they want to ensure was hit during simulation, immediate asserts and cover statements can be utilized. These assertions and cover properties will propagate to the generated RTL as part of the HLS process. And whereas most Verilog users prefer to see them in the form of system Verilog assertions, you can also have Catapult produce PSL or OVL assertions instead. And this is just the first of several examples of taking verification constructs we are familiar with at the RTL level and applying them to the HLS design source. And it is a useful debug technique, especially during RTL integration level testing. Broadening our dynamic simulation scope to now include metric-driven high-level verification, and for starters mentioning that though all the DPD verification shown thus far was done on a C++ design source and test bench, the approaches outlined are applicable to many different and various verification environments. For example, the screenshot to the right demonstrates instantiating the DPD HLS C++ as a DUT within a vanilla UVM 1.1d System Verilog UVM test bench. While I advocate for thorough and rigorous HLV, using known and trusted verification techniques supports a wide range of verification requirements. Again, the only difference with HLV is the DUT is at a high level of abstraction. In mentioning reuse, as depending upon the environment, various pieces and parts up to and including the entire test bench can be reused for efficient and predictable post-HLS RTL sign-off. Further motivation as to why to perform HLV, mentioning the Google presentation on their video coding unit at Hot Chips last August, where they mentioned that 99% of the functional bugs were found in HLS-ready C++ before running any RTL simulation. RTL code coverage has been around for a long time. And with Catapult coverage, we're bringing RTL coverage concepts into the HLS world, essentially treating our C++ or System C design source as a hardware representation and producing RTL-like coverage data as a result. With Catapult coverage, we can measure statement, branch, and expression coverage data based on a pre-HLS design source. We can even embed functional coverage model in our C source that will ultimately be rendered to look the same as what you'd expect to see in a functional coverage model written in System Verilog. A key thing to note when it comes to tracking code coverage against C++ or System C HLS designs is to keep in mind the sorts of hardware structures that are going to be created as part of the HLS process. For example, if you have a loop in your C source, that will, based upon user directives, often show up as a multiple blocks of logic operating in parallel, with each block running as one iteration of the loop. From a hardware code coverage perspective, just knowing that you exercise the entire loop in C isn't good enough. You want to make sure that each iteration of the loop was fully exercised, especially if there are branches or conditions within the loop that will behave differently depending upon which iteration of the loop you're on. This is an example of how catapult coverage is producing HLS-aware data, and the resulting coverage data will treat each iteration of the loop as separate elements, more closely mimicking how the resulting RTL coverage will look. What this means overall is you can focus your coverage closure efforts, both coded and functional, against the pre-HLS source with the expectation of having very few surprises once you proceed to the RTL integration and sign off. Not surprising, we can even go so far as to achieve traditional verification coverage closure on our HLS design source. Achieved using known and trusted approaches such as running regressions and collect coverage metrics via an industry standard, the UCDB. This provides us with the needed and expected verification management capabilities, including the ability to analyze results, generate desired coverage reports, and create and apply desired exclusions. We can also merge results from the multiple tests, rank them, and also integrate our test plans, all as we track progress towards our verification requirements. Shown here are the preliminary results from our dynamic verification on our DPD block. And a reminder, all of this, including both the code and functional coverage, has been done at the C++ design level of abstraction via our C++ test bench. Noting, for example, in the code coverage, we see the hierarchy of the HLS design as expected from our HLS-aware code coverage capabilities, thus providing us the ability to correlate these observed results with our post-HLS RTL coverage. In summary, we've walked through the catapult high-level synthesis and verification tools and associated methods that allow us to focus our design and verification efforts at a higher level of design abstraction. How high-level language and HLS allow us to design bit-accurate hardware, with results from the DPD show that the HLS design is 600 lines of code, representing a greater than 10x reduction compared to the equivalent RTL. And how the use of high-level verification, including known and trusted techniques, such as static and formal methods, along with metric-driven dynamic verification, combined with the efficiencies obtained by operating at the higher level of abstraction. Results from the HLV simulations of the DPD HLS model show it runs at a speed greater than 300x faster than the equivalent RTL sims. And while we don't have time today, noting there is a follow-on chapter regarding verification sign-off of the post-HLS RTL, yet this is predictably and efficiently achieved via our HLV investment, resulting in a push-button, no-surprises sign-off. Before we move on, a thank you to my colleagues John and Esamate for their help in both creating and reviewing this material. And finally, recognizing that today's SoCs are designed using a combination of approaches, including HLS and handcrafted RTL, addressing the verification crisis also means identifying ways to reduce issues in handwritten RTL, such that the fixed simulation cycles every project has can be used most effectively. Kurt Takara now joins us to lead us through what an RTL intent-driven verification flow with the goal of reducing the bug density in RTL looks like.
Thanks, Dave. Functional verification is a given. Everyone knows it and knows they need it. Simulating until you're done is a tried and sometimes true methodology, remembering back to Harry Foster's introduction regarding the verification crisis. This is used to find a bunch of design issues and fix them before a design gets into a customer's hands. But going back to Harry's introduction, let's think about those 3 pillars of design. Harry's prescription to get us out of the verification crisis includes, first, reducing bug counts and bug density from the start. Let's think about areas where bugs exist in the development process. They're found everywhere from simple coding errors into design construction errors, then functional errors, items where the implementation of algorithms or the architectural specification isn't correct, and there are unintended interactions, and even where there are initialization issues. Finally, Silicon is always one piece of a system, so there are system design and hardware and software interactions to consider. Every project has a finite set of compute resources and simulation licenses and calendar days to get done. Reducing bug density up front with correct by construction techniques in the produce pillar Harry spoke of to the intent-focused insight in the proof pillar will make that functional verification simulation part of your project more effective. It's a good start, at least, in ensuring that those finite simulation cycles you have will be impactful. But they're not sufficient. There's another class of issues that aren't found in simulation that impact design success, such as clock domain crossing issues or hidden functionality and Trojan attacks, to implementation issues that corrupt designs downstream in implementation, whereas the RTL itself was clean. Let's break down the different capabilities of a correct by construction and intent-focused, insight-based verification flow, aimed at the goal of reducing bug density in RTL. It begins with code analysis early in the design stage, often run during design. These focus on finding simple to complex RTL coding mistakes and ensure the design is properly and efficiently initialized. The next set of capabilities is aimed at verifying some of those items that can't really be verified in functional simulation, such as clock and reset domain crossings as they pertain to asynchronous operations. These test specialists' verification capabilities can also review the design construction, verifying that register operations as coded implement the design intent, and that interconnects are correct between the myriad of IP blocks integrated in today's SoCs. It's also possible to confirm that the design implements the specification with capabilities aimed at cross-checking design versus specification, then check completeness, exposing potential Trojan attacks. Finally, as designs move through implementation, they are changed and the design drifts from a known good source. Capabilities exist to verify that the implementation keeps the design true to the original intent. All of these capabilities together build a flow that supports Harry's prescription for solving the verification crisis, deploying verification capabilities early to produce, prove, and protect designs to meet intent. Static code analysis are used in this methodology to find simple RTL mistakes and review for initialization vulnerabilities. The types of issues that are found in these analyses can be broken down into syntactical, semantic, stylistic, structural, sequential, and specific categories. Syntactical checks and even some semantic checks are performed typically by compilers. Linting performs the first 4 of these types of checks. Advanced linting finds sequential issues based on deeper functional understanding made possible through the use of formal engines. Finally, further automated formal analysis is done on the RTL with initialization X-checking to identify likely unintended, uninitialized portions of the design, as well as portions of the design that are subject to X-pessimism or X-optimism, problems that might normally be identified much later in the development process. Linting tools analyze the RTL and identify a range of design issues, some of which may be detected during simulation, but perhaps taking more time for triage, while others may only be detected in later stages of the design process, such as during synthesis or implementation. Because linters require no other input than the RTL and use static analysis techniques rather than time-based functional analysis, the time to get results is typically very fast. The type of issues identified by linting can be split into 4 main areas. We'll trust that syntax issues are obvious and don't need examples. Lint finds syntax issues in the process of compiling code. So let's focus on the other 3. Semantic issues occur in syntactically valid RTL code, but where the elements do not make contextual sense. These may cause problems in synthesis or mismatches between the synthesized netlist and the original simulated RTL, such as invalid assignments from one RTL type to another. Structural issues are found when looking at the bigger picture. For instance, operations between objects of different widths, FSM issues that may cause the state machine to lock up or never reach a particular state, RTL that will cause latches to be created in synthesis, and so increase testability challenges later, inconsistent clock and reset styles, such as a mix of synchronous and asynchronous use of a reset, and RTL code that will never be used, perhaps because a condition will never be reached. It also includes connectivity issues within the design, such as undriven inputs, outputs connected together, combinational loops, and objects such as clocks and resets also used as data inputs to flops, as shown in the schematic on this slide. Stylistic issues are the simplest type of checks, covering aspects such as the presence of corporate headers and adequate levels of commenting in the RTL. Naming conventions to make the RTL more understandable, objects that have been declared but are never used, and aspects that improve the maintainability of the RTL in the future. Advanced linting tools build on simple static lint concepts and serve an important role in intent-focused verification. Providing deeper insight than simple static analysis, these tools are able to leverage their exhaustive exploration of the design state space to identify issues that would not otherwise be apparent. Equally important, these tools are able to eliminate false violations, allowing the team to focus on real problems. Let's look at these two code examples. Starting on the left, there is an issue in red where in state B100, the next state can never be anything but the same state. This is a coding error, and the state machine will deadlock. A static linting tool can catch this error, as no deep functional knowledge is needed. This type of issue can be caught in a manual code review. The code on the right, however, may still not be free of deadlock. Notice that the code has changed in the if clause from B100 to B001. Therefore, a deadlock may not be possible, and a static linting tool would not flag an issue. However, whether or not there is a deadlock depends on whether or not the signal RTN can ever be a 1. If it's always a 0, there is still a deadlock. Deep functional analysis in advanced linting tools will exhaustively analyze the state machine to determine if RTN can be a 1 to break the deadlock. Moving on to the sixth and final check mentioned a few slides ago, we check if the code is specific. Are all the items defined where needed? And will the design behave consistently? Developing a design that is clean with respect to initialization and X-propagation issues is important. There are a number of issues with simulation regarding X-optimism and X-pessimism which cause missed bugs and delays in verification. Hence, it is important to have an X-verification strategy in place, ideally before the design is integrated into the simulation environment. Most designs will have some uninitialized registers or other X sources. The goal is to make sure that these X sources don't corrupt registers that were initialized or other control logic such as outputs, FSMs, and clock reset trees, to name a few. The analysis should not have the same limitations of optimism and pessimism seen in simulation. The X verification flow is straightforward. It operates on synthesizable designs. An initialization sequence is applied and formal analysis is done to check for X corruption. Part of this verification reports X sources, typically uninitialized state elements. These X sources can also include buggy behavior of the design, such as X assignments in the RTL and multiply driven buses, to name a few. Initialization is also reported showing registers have an X value at the end of the initialization sequence. This is reviewed by designers to ensure the design is properly initialized. The expected X sources are then formally analyzed to ensure that they don't corrupt initialized registers and other control signals. The exhaustive nature of formal analysis ensures that if there is a way for X to corrupt some good logic, it will be found. With all these X issues cleaned up, the block will have a smooth transition into downstream verification flows. Here is an example of a design which contains registers without resets, which might be part of a data path, and registers that have been reset, which would be part of control logic. Part of the analysis can identify the registers that don't have a reset. At initial power up, all registers in the design would be in an unknown state. As the reset is applied, the registers with a reset are initialized while the other ones are not. As the init sequence completes, an analysis is done, reporting all registers which are uninitialized. This is investigated to ensure a correct initialization sequence. As the design comes out of reset, proper operation of the design is analyzed. In this case, you can see that the X value in the top left propagates to the register on the top right, and the register on the top right receives a known good value. The two registers that were initialized also receive new data. The one on the lower left receives good data. The one on the lower right, however, is corrupted from the X value in the upper left register. This points to random behavior that would happen in silicon. Steps would need to be taken to prevent this X corruption from happening, either initializing the upper left register or improving the blocking logic for the lower right register are two possible options. X verification is a vital step to ensure that the design in silicon behaves as intended. The easiest and earliest capabilities of this flow are now behind us. The issues we've discussed so far can eventually be found in simulations with enough stimulus and time. However, let's move on to a class of issues that aren't found by simulation. These are asynchronous boundary issues. An asynchronous boundary issue occurs when the sampling device downstream from the boundary receives a signal transition that doesn't meet its setup and hold requirements. When this occurs, that sampling device, like a flip-flop, resolves to an intermediate state for a non-deterministic value. This is a well-known phenomenon across asynchronous clock boundaries and even with asynchronous reset boundaries. The solutions are also fairly well known, but the challenge with these crossings is that they are difficult to find and implement with certainty. In this example, we show the three main types of CDC issues. First, there are structural violations that occur when the synchronization structure is missed or incorrect. This will lead to metastability on the CDC path. Second, there are protocol violations that occur when the synchronizer protocol rules are violated. This will lead to data loss, data corruption, or metastability even though the synchronization structure may be correct. Third, there are reconvergence violations that occur when there are timing dependencies between two or more CDC paths. This will lead to functional race issues in silicon. Static analysis is used to verify these synchronization structures. Second, assertions are used to verify the protocol rules in formal analysis and simulation. And finally, metastability delay models are used to verify reconvergence in simulation. CDC protocols can get quite complex. Performance, power, and area constraints, as well as the need to send wide data across asynchronous interfaces, complicates the matter and forces the implementation of some very aggressive and often confusing designs. A synchronization scheme requires a specific protocol to be followed. The simplest is that of a single 2DFF serial register combination. The required protocol is that the source signal must be held long enough for the destination flop to sample it. This might seem trivial, but it is often overlooked. Verifying the protocols is important to ensuring correct behavior. When the protocol is violated, data can be lost, corrupted, or even metastability may happen. Simulation will typically not find this, but your customer will with intermittent failures. Portions of CDC protocols can be verified without simulation. The RTL is examined statically for the presence of synchronizers and synchronization schemes. Assertions are automatically generated to ensure that the protocol is followed. Advanced tools such as Questa CDC can do deep formal analysis on these assertions versus the RTL to determine if the protocol is followed. In some cases, these assertions cannot be formally proven, and they are promoted to a test bench-based simulation and coverage flow. In those scenarios, these assertions are either covered or they are not. If they are not, the verification is incomplete and additional testing is needed. In addition to CDC, there is another class of asynchronous behavior that can cause issues and will not always be detected in simulation. These are reset domain crossing issues, or RDC issues for short. For example, consider this circuit. If there is a different asynchronous reset on each of these flip-flops, the downstream flop can have its setup and hold requirements violated and go to a non-deterministic metastable state. It is an issue if RST1 is asserted while RST2 is not asserted, but it is not an issue if RST2 is already asserted when RST1 is asserted. CDC tools are capable of verifying the issue where the clocks and resets are both asynchronous, as identified in the middle row of the table. However, if the clocks are synchronous, there will need to be a violation reported or the need for an evaluation depending on the constraints applied regarding reset ordering. Tools such as Questa RDC exist to verify this phenomenon. Having now discussed the asynchronous operations, let's move on to consider how the capabilities of an intent-focused verification methodology might help eliminate construction bugs in the design before they're caught in simulation. One type of construction issue that might occur is an interconnect issue. Today's SoC designs have a high number of connections. Most chips are pin limited and thus require a pin mux to share pins with various functions. There are various other connections, from power to control to clock and reset trees, to name a few. Verification of these connections is important to ensure trivial bugs don't sneak into proper functional verification. An intent-driven verification solution naturally must include verification of connections of ASIC and FPGA designs from the block to the SoC level. Typical connectivity checks include direct connect, conditional connections, delayed versions of both, as well as connections to constants. The flow starts with a specification, which is described in a CSV file, or with a connection type property. If the user doesn't have this specification, then often a reverse connectivity spec can be generated from the design. Wherever the specification comes from, properties are generated and the connections verified against the design, in some cases structurally and in other cases functionally. Using formal to verify your connections has many benefits over using simulation. The specification is straightforward to create, and once the flow is put in place, any change in specification or design, the connectivity verification can typically be completed in under an hour. Since formal is being used, all types of bugs are found due to the exhaustive coverage of the state space. Here is a simple example design showing some direct and conditional types of connections. A specification describes the expected connections of the design. Here you can see a direct connect from IAO1 to OUT1 and a conditional connection from IAO2 to OUT2 when the select is 1. The specification is converted into properties. The CON1 property says that IAO1 is equivalent to OUT1, and the COND1 property says that when cell input is 1, the IAO2 is connected to OUT2. These properties are then formally verified with bit-level accuracy. Formal efficiently explores the full state space of the connections. The formal result will be proofs or failures. In this case, the first property is proven and the second one failed. For the failing property, the issue could be an incorrect specification or a bug in the design. This needs to be analyzed and corrected as appropriate. Using formal to do your interconnect verification is the most complete and efficient method for doing this kind of verification and avoids the large number of simulation cycles needed to test connectivity. Another type of construction issue that might occur is a register specification and implementation issue. Most designs have a collection of configuration and status registers, which are accessed through a memory mapped interface. Typically, this interface is a standard bus interface, such as an APB bus or even some custom bus interface. The goal of the designer is to ensure that these registers are functioning correctly, both from an address and data path analysis, as well as a policy for each register. There are typically two main types of specifications which describe the register policy: IP exact and UVM. Each is slightly different in how the policy is specified. Typically, policies include read-write, read-only, write once, read-to-clear, to name a few. The specification is read and property checks are created, which are then formally verified. Transactions happen on the bus interface, and the register is verified to ensure correct address decode and data operations, as well as policies are adhered to. Verification can be done through the interface, a front door access, or checking at the register itself, a backdoor access. The flow for memory-mapped register verification begins with the synthesizable RTL and a specification describing the policies for each register. Each register specification has a number of properties generated for it. These properties are then formally analyzed, and results are either proven or failed. Types of checks that are done include register initial values, address decode, data muxing, register policies, and more advanced internal conflict checks, which include volatility. Formal is more efficient and exhaustive for this type of verification than simulation. Not only is correct operation investigated, but due to the exhaustive nature of formal, the full address and data space is explored to ensure each register is only accessed with the correct address, data, and policy. Here is an example showing some registers that are mapped from an APB bus interface. The specification will list information for each register, some of which includes address offset, init values, policy, bit size, and location. The specification is converted to properties which check this information for each register. The result of the property is proven or failed. Each register specification will have a suite of properties checking the various functions. The R1I property is proven and verifies the initial value of the register. The R1W property is proven and verifies that for a valid APB write to the correct address, for R1, that the data is correctly written to the register. The R1R property is also proven and verifies that for a valid APB write to the correct address for R1, that the data in R1 makes it to the APB data out port. These two properties also verify the read-write policy for this register. The R1N property failed. This checks that for all other transactions not related to R1, that R1 remains stable. In this case, there's a bug in the address decode such that incorrect data was written into the register R1. This shows the power of formal in verifying both correct operation as well as ensuring illegal behavior is caught. Having now discussed construction issues, let's now consider how the capabilities of an intent-focused verification methodology will be able to verify that a design conforms to its specification. Assertions such as System Verilog assertions, or SVA, are language semantics that help capture and verify the design intent. Operational assertions, on the other hand, propose a complementary coding style that capture the design's functionality as a set of operations. In the operational assertion-based verification, or ABV approach, the functionality of a design is split into different operations. With each operation exhaustively verified, operational ABV checks that there are no gaps between the operations of the design and that the design's functionality is fully verified. In this context, we consider an operation as any single or multi-cycle activity of the DUT, such as a read or write operation of a DMA controller or the execution of an instruction of a processor. An operation is described by the following aspects: start state, a condition describing when this operation can start, a trigger condition, an event that actually triggers the operation, expected output behavior, the values that are expected to be seen on the output signals of the DUT. End state, how the operation is reflected on the internal states of the DUT. Timing diagrams lend themselves well to operations and are often used to capture operational assertions. Operational assertions can be written in the one-spin language called ITL or in the standard system Verilog language. One-spin provides title, which stands for Timing Description Assertion Library, a library wholly written in SVA. In the example shown, we have a simple operation that starts at time point t. The start state is wait, the trigger condition is transfer going high, and the operation succeeds when the signal complete also goes high at the time point we choose to call t complete. At that point, the design state becomes finish. In title, we describe the t-complete time point as an SVA sequence t-complete using the next function provided in the library. So t-complete is 4 cycles later than time point t. The operation is then captured as a property transfer. At time point t, we describe the cause as being the state is wait, and the trigger is transfer going high. The effect is described using the implies keyword and specifies the state should be finish and the signal complete high at time point t underscore complete. The operational assertion is then captured as the usual assertion property semantic in SVA. We can then proceed to formally read and verify this assertion in our one-spin product. In order to detect verification gaps or achieve complete verification, all the operations of the design need to be captured and verified. And in addition, the sequencing of the operations is also verified. This forms the basis of the one-spin operational ABV methodology, which is also known as gap-free verification, that we'll discuss in a couple of slides. Thinking about applying gap-free, let's look for a moment at processor verification with a focus on Trojan detection. In other words, the implementation does everything it is supposed to do and does not do anything it is not supposed to do. Here is a suggested overall flow. A normal formal verification of a processor model will have a design analysis engine. Assertions are then generated based on the design. These assertions not only cover the standard processor model, but also any custom extensions that you may have added. You then end up with a full database that contains everything pertaining to the ISA of your core and to the verification of your core. This information is then used to generate the assertions automatically. The database of assertions is then run through the formal tool flow to get full proofs or failing assertions and debug cycles, and of course the integration with the coverage database. Applying one-spin gap-free verification to the processor verification flow, one is able to move beyond proving equivalence between the RTL and the set of operational SVA. It also verifies that the set of assertions is sufficient to cover the RISC-V core design and ensures that there is no unverified RTL code. Any extra functionality in the design, including hardware Trojans, is detected and reported as a violation of the ISA. This includes the systematic discovery of any hidden instructions or unintended side effects of instructions. This enables both core providers and customers to have the highest confidence in the RISC-V core implementations. In this example, it is possible to extract register mappings automatically from unreadable machine-generated code, such as SAIL, eliminating manual effort. This can detect all issues in the instruction set, as well as find what you are not looking for, as was the case with an undocumented cease instruction that ended up in the code of an existing processor. Standard verification methods will not be able to detect this, as the focus is only to prove what is there and not that what should not be there is absent. Having considered how a design can be verified to implement just its specification and nothing extra, let's move on to the last capabilities of an intent-focused verification methodology, that of ensuring that the intent is still met throughout implementation. Let's begin with synthesis. On the left side of this diagram is a properly implemented clock domain crossing synchronization scheme. However, during synthesis with power, performance, and area constraints, requiring significant transformation of the design, it's possible to have a netlist of the design still be functionally correct, but be timing sensitive to transitions. In this example above, the synthesis tool has built a logically equivalent representation, but timing races between the two paths highlighted in red may result in offset transitions on the final or gate design that will create a glitch. This glitch, if sampled in the downstream flop, will result in metastable behavior just as if it had been a poorly designed synchronizer. Synthesis and place and route can also compromise FPGA flows, but FPGA synthesis is different from ASIC synthesis. For synthesis to achieve optimal utilization, you have to deploy FPGA-specific optimizations like constant register removal, register duplication and merging, pipelining, retiming, FSM reencoding, distributed block RAM-ROM, RAM implementation of SRLs. And so, the equivalency checking problem for FPGAs needs to be addressed with both combinational and sequential equivalence verification. As depicted in the tool flow, after design setup, smart mapping identifies where best to use combinational algorithms and where a sequential algorithm will be needed to check for aggressive optimizations. The compare stage orchestrates these algorithms and either identifies a full equivalence or pinpoints differences between the golden RTL and the netlist. Finally, we have explored many of the capabilities of a test benchless verification flow, focused on verifying that the designer's intent is met. Removing these issues from the design before entering simulation is a key part of Harry's prescription for addressing the verification crisis that we are in as an industry. Allowing designers to verify that the design meets the design intent and specifications before a single verification cycle is used from the finite simulation budget allows simulation cycles to be used for more challenging functional issues, certainly awaiting. Let's revisit our original slide showing the nature of bugs, both those caught in simulation-based verification and those that can't be found in simulation. The capabilities of intent-focused verification, fueled by static and formal technologies, allow teams to find and address many of the issues identified as being caught in simulation today. Going back to Harry's premise of addressing the verification crisis through producing clean design, proving intent, and protecting to ensure design intent, these capabilities have freed the simulation cycles to focus on the remaining functional errors, as well as system design and hardware-software interaction. In addition to RTL intent-driven verification, hardware-accelerated platforms have become indispensable due to the increasing size of SoCs and the necessity of running real software applications before tape-out. Amir Aderha will discuss the Siemens EDA Veloce emulation and prototyping solution.
I'm Amir Aderha, product manager for Veloce Power app with Siemens EDA, and I'm very excited to present Veloce emulation for this session. We offer a complete emulation and prototyping system as shown here. On the top, you see our software apps, which address customer challenges for different categories of problems. They are customized and efficiently designed to address the specific challenge. For instance, our DFT and fault app focus on design for test and fault grading. PAVE 360 is a solution which addresses automotive market. We will discuss further some of the apps during this presentation. In the center in green, extended virtual and edge solutions are shown, which are vertical market oriented. Below that, the OS is shown. The operating system is the main control software that enables the design to map to a specific hardware and run. And at the bottom, you have the hardware platforms with different flavors based on performance, requirements, and capacity. On the left, you have Veloce Strato Plus, our latest emulator. Veloce Primo is our enterprise prototyping platform, and Veloce Pro FPGA, which helps with desktop prototyping. The concept is really software workloads enabled by running software apps by vertical market with an operating system mapping to the hardware platform. The platform is designed for scalability, from custom crystal chips to boards to entire system and software. All is designed and implemented in-house in Siemens EDA to provide a comprehensive hardware-assisted verification platform. Scalability does not limit to one aspect. It applies to entire flow of your work. It's addressed from compile time, runtime, throughput, and debug. For instance, fast compile time leads to fast turnaround time for you. The co-module bandwidths that we have and the number of co-module channels that we have enable you to have high throughput. And full visibility enables you to have great debug experience. Veloce accelerates progress cycle by predictability, reliability, and efficient debugging. Each compile time that you do is first pass success, fast and reliable compile. You will have fast design download irrespective of design size. Your run, every time you run, you will get the same result. You will have capabilities like offline monitor and very fast, high bandwidth interface channel to Veloce to enable you to get fast throughput. On the debug side, you always have 100% visibility to entire design. So you can see the whole design and you can debug it. As verification engineers, we always make mistake. And to rectify that one, with incremental force and ECO compile, when things go wrong, you can easily add them, or if you forgot them, and recompile. And in a matter of minutes, you can have extra force. Or a matter of an hour, for the full SoC, you can have a new compile. Veloce Estrado is really architected to scale. Low latency, high bandwidth channels, independent co-module channel for each AVB over advanced verification boards. And you're able to run concurrently your test bench, your communication, and your design on the test. All these great features enables you to have seamless virtual environments, great time to visibility and debug. This platform enables you to have very smooth simulation acceleration environment to be able to do coverage closure. Monitors and trackers can be enabled for data collection without feeling the high impact of performance. And for power trend analysis and measurement, you have full visibility and data and high bandwidth to get that data out of the emulator. And the beautiful part of it is, as you go to bigger and bigger design, this is scalable, and you will not get no performance or throughput degradation. Another attribute that I wanted to discuss is clock frequency versus throughput. Hardware acceleration verification always comes to what is your turnaround time. So how long does it take to complete your test to finish, and how long does it take to debug? And as you can see in this table, in some of the competition platforms that they have higher clock frequency, but the runtime eventually is shorter than Veloce platform, and Veloce platform consistently outperform them. So you want to focus to end-to-end vault time rather than just clock frequency by itself. So Veloce Estrado's superior system architecture delivers more software-driven workload performance, even when the competition reports faster clock speed. This is on top of a great compile time. As you can see in this table, compile time of 12 hours versus 3 hours on the same design. And obviously our debug, which is very appealing, 1 million cycle in 5 minutes. Ensuring optimized and productivity debug with Veloce Strado. Whenever you are working on a design, especially like SoC level, debug is a key factor to your productivity. With Veloce Strado, you're always, with every compile, you have full visibility to your design. There is no model performance degradation impact. There is no increase of capacity. Inherently, you will get visibility because of the design of the architecture of this crystal chip and the whole system. You will be able to upload for long simulation. For instance, 1 million cycle upload in 5 minutes, and this is irrelevant of the design size. The whole architecture allows you to, for a small or big design, you get the same number. In addition to that one, you have live stream capability, which allows you to send the information for your key elements outside the emulator without getting any degradation on the performance for the entire running of your test. Advanced debug flows also are available, like checkpoint, save and restore, and backup replay, and they can greatly improve your efficiency. Any complex protocol or system, especially when you're running a SoC level, you need a good protocol analyzer to debug. And we have, for both virtual and ICE, great protocol analyzer for almost all the major protocols. Our triggers do not require extra compilation step, and they enable you to trigger your desired time. And recently we implemented virtual FSDB support, where it allows you to generate FSDB much faster. So in summary, you can have 1 million cycle with full visibility, which takes 5 minutes, irrespective of your design size. On the design and verification milestones, you can see that if you look at the different design and verification milestone, we start with IP, block subsystem verification. Then we move to SoC integration, booting the OS, software verification, and silicon bring up. A lot of different semiconductor companies have very defined steps. The first is virtual platform. The second is IP block level RTL. Third is the SoC RTL becoming available. Number 4, SoC RTL is completely stable. Number 5, the RTL has been completely debugged. At this point, we have moved to gate level, and now you have a gate level netlist available for the full SoC. From here, you start backend implementation, and you have tape out, and then the chip is back where silicon is available. The market dynamic that we see is that there is a need for a right tool for right task, and you need a complete offering to help you with all these necessary steps. On the hybrid virtual platform, we offer Veloce Hicon. There is a need for virtual model software workloads and very good and strong integration to hardware-assisted verification and running fast. Veloce Hicon is the only solution in the market enabling early software workload analysis. It is completely integrated with Veloce hardware-assisted verification platform offering. If we look at the emulation domain, we start with the RTL emulation with Veloce Strado and or Strado Plus. Here the key is RTL debug and visibility. You need broad use models, and you need to scale in capacity from basically subsystem block all the way to full SoC. When the design becomes more mature and stable, you need to look at power flow on the emulator, which you can do with Veloce Strado and Strado Plus Power App. What is key is still visibility, workload capability, and scaling, and integration to Power Tools. We are introducing Veloce Primo as the next step, which is an enterprise FPGA prototyping platform, and the concept of emulation offload. When a design reaches a certain level of maturity, where the ability to debug is less important, but you need speed, you offload certain tasks from Veloce Strato emulator to the Veloce Primo Enterprise FPGA prototyping platform. You need speed, you need software workload compatibility with the emulator, and you need capacity scaling because you can handle full chip. Then when you move closer to gate level and tape out, we need to be able to do gate level emulation. We are very close to silicon behavior at this point. We have with Veloce Strato and Strato Plus a strong gate level flow, and you also need to scale in capacity because you are doing full SoC at this point. Next step is the desktop FPGA prototyping with Veloce Pro FPGA. It is a lower footprint capacity. It is more of a /lab/desktop type of environment. Here, ease of bring up and complete type of use model from virtual to ICE are key. And it has to be fast because targeted for software and silicon bring up. This offering is the complete and integrated solution. And you can see that Siemens EDA now has all the pieces of the puzzle for verification and fully integrated into a single Veloce platform. This is a complete platform that provides the right tool for the right task. Veloce software workload and benchmark requirement with hardware-assisted verification is used to satisfy workload and benchmark requirement. You need a hardware-assisted verification environment for three fundamental reasons. The first one is the workload and benchmark requirements are running very long software sequences, which takes an extensive number of verification cycles. So the length in number of cycles of the workload is extremely large. Power and performance analysis for those frameworks and workloads is very important. To do it, you need accurate power and performance analysis during the workload and the benchmark cycle, which requires visibility, for example, the power activity. If you cannot monitor everything very accurately, you cannot capture power activity. You also need to have comprehensive debug tools so that when you look at performance, for example, you can understand where you have any issue. So power and performance analysis requires certain kind of hardware. Third one is size and complexity of the SoC. We are talking about billion gate design. For instance, AMD EPIC server is a family of very large chips that were used on Veloce Strato. We are talking about many billions of gates on a single design. So the complexity and size of what the hardware assisted verification tools needs to handle is extremely large. What is interesting is that the hardware assisted verification for our semiconductor customers and partners is the only option when hardware and software meets. You have the real software workload running on the emulator. Another aspect that we want to discuss is using the virtual platforms. As your designs get mature, you add more to the hardware side. So SoC level verification and early in the design cycle, it seems contradictory. But if you think about your subsystem, although the other pieces are not ready, you can use a virtual platform like Veloce HiCon to use the CPU and RAM model and the other pieces from the configurable Veloce Icon and start running the real application very early on the design cycle before the SoC even gets ready. During that time, you can measure power, you can profile your power, you can look at your heat map, your performance, and if you need for the debug, you can utilize the code link to look at both your software and hardware and waveform and your power profile all together. And as you progress during your design cycle and your SoC become available, you can take out those pieces and incorporate your SoC to extend your level of verification. Veloce app offering is very extensive. You can see the list of Veloce Power app, and the beauty of each app is it is really targeted for a specific application. So they are very easy to use. They are very easy to get integrated to entire flow, and they address very specific issues that customers are dealing with. I'm going to discuss one or two of them during this presentation. So let's look at Veloce Code Link. Veloce Code Link is our trace-based approach for debug. It is used as an environment which allows you to have traditional debug view into the processors being run an emulation session. It does this with no changes to the software running on the processor and with no changes to the design you are working on. The setup is simple and easy. You only need to add a monitor to your test bench. CodeLink allows you to perform your software debug offline, freeing the expensive emulator for other work. We've also made modification to CodeLink to support large output traces that will come with the emulation. So from this view, you will see your waveform, your actual application running on the processor. You can see the assembly of it. You can see the register view of it. So it is truly a hardware-software co-verification platform. Also, I would like to introduce you to Veloce Power app, which enables you to run real scenario and workload and consider it for the power analysis. Veloce platform, without requiring any extra compile, just with the Veloce Power app, enables you to do power profiling at hundreds of kilohertz. You will get the power profile and the heat map, and based on that one, you can find the interesting area for more analysis. So you can find which benchmark are really interesting for power analysis and where for each benchmark you can focus. In addition, we produce some metric-based power tracking like clock gating efficiency and flip-flop efficiency that can enable you to reduce your power waste at the SoC level. And we are talking about generating this data at hundreds of kilohertz. After you have decided which area to focus further, you can generate in two flow in the middle side with the power analysis and optimization. You can have a file based, like a traditional, you generate either SAFE or FSDB and feed it to power tools and get the average power or peak power. Or you can use the Veloce API flow with Power Pro and Power Artist, which is 10x faster, enables you to have 10x faster time to power. This is available for millions of cycles. And at the right column, you can have sign off power, and that can also be file-based with the SAFE or FSDB, and you can feed it to Power Prime Power or Power Artist or Power Pro, or you can use the API flow. The API flow is working for Power Artist and Power Pro, with the prime power is work in the progress. But what you see as overall is a complete solution from profiling your power at the design for the design teams, doing the power optimization by providing clock gating efficiency and flip-flop efficiency, and making the power metric driven, and then moving on to the power teams where they can dig deeper and look at the power data from the power team perspective, and also for sign-off. This concludes my presentation. I appreciate your time, and now I will be available for questions.
Now, before the live Q&A, let me wrap up today's tutorial by summarizing what we discussed. A common theme throughout today's tutorial is based on a design plus intent methodology, which significantly improves a project's verification debugging efficiency due to the reduction in bugs during RTL handoff. The first pillar we discuss is the produce pillar, with the goal to produce correct intent by construction. And here we focus on high-level languages and high-level synthesis, where we saw examples of an order of magnitude reduction in the code to describe the design, which in itself would result in an order of magnitude reduction in bugs per line of code, as I discussed in the introduction. Of course, there's an additional benefit of orders of magnitude speed up in simulation using higher-level language. So this results in efficiency gains by designing and verifying using higher level languages, and productivity gains using predictable post-high-level synthesis RTL during verification sign-off. The second pillar that we discuss related to our design plus intent methodology focused on proving that the intent is met. Here, we explored many of the capabilities of a non-simulation based verification flow. The goal here is to remove issues from the design before simulation and regression testing begins. This allows others to verify that the intent of the design is met before a single cycle of simulation is performed. That in itself frees up those important cycles for the more challenging functional issues. And finally, we discussed the protect pillar of a design plus intent methodology. And here we focused on emulation, which has become critical in the age of SoC verification and validation, particularly as the amount of software content increases throughout the development lifecycle. Next, let's open it up to David, Kurt, and Amir to answer your questions.
Thank you, Harry. Just checking the chat. Hi, I see a question from Aerne, assuming you folks can hear me, regarding what is a good way to get training on verification using System C. And Aerne, it's almost like maybe there's a follow-up session matchlib in System C. I believe it's at later this morning. I'd have to check the exact time. Maybe John Kraft can help give me a chat on when that is. It's basically a follow-up session to today's DVCon tutorial day, where is essentially verification specifically around HLS System C, but in a System C environment, and that's using the NVIDIA matchlib.
Yeah, it's after the break, starting at 11:30 Pacific.
And I didn't plug him to make that question. That was interesting.
Good job.
No, we certainly recommend start that. Hopefully you can join for the session after the break. And if you don't have your questions answered, we can follow up with the folks there. I think I'll just take that opportunity. You don't have any questions pending, in a sense that, you know, we've talked about designing in high-level languages, HLL, as Harry mentioned, including C++, untimed C++, and System C. System C we sometimes encapsulate as a clocked System C because it will have a clock associated with it. And certainly some trade-offs regarding those two languages as input to high-level synthesis. Both give you that higher level of abstraction and give you some of the benefits we've talked about today. You know, fewer lines of code, faster execution. Though, as with many, there's a greater detail, I would say, in a clock System C, the support for multiple threads. You can perhaps do more control-oriented things. So it really is dependent upon, this is a follow-up question I see Jonathan asked, is C the right language? And it depends on, like with many questions, it depends on what is it you're trying to model. And if we would think that, for example, C++ or System C is the right language. And admittedly, in some, you know, control-heavy logic, RTL is still the way to go. You may not necessarily gain any things by describing in necessarily System C, excuse me, you know, a clock black clock level protocol. So the quick answer is it depends.
Python or YAML.
There's the comment in the chat about Python, YAML, or JSON. You know, we certainly see activity, obviously Python, in terms of test bench components, modeling in Python. And that's, I think, becoming more common. Don't see it in terms of a design entry language. There's a follow-up comment about high-level architectural definitions, and yeah, I understand the comment. There was a metric that so many engineers today, younger than myself, but they speak Python, you know, like the back of their hand, in contrast to the number that speak System Verilog. So if we can, you know, the motivation to say, hey, can you define architectures in a language such as Python? Certainly understandable. We can give it another moment, but I don't know if there's any other questions. Oh, sorry, there was a comment I missed about System C used in UVM environments.
That may have been a response to the question about way to get training, mentioning webinars from Doulos.
Yes. And I'll take that as a entry point to say, you know, it is, I mean, not to be too much of a geek here, but interesting environment in a sense. What we've talked about today, hopefully one of the takeaways is in terms of HLV is working in your known and trusted environments, your SV UVM environments for the DV folks out there, and the ability to plug in HLS models, you know, such as System C based HLS models in those environments, we feel is a compelling use model. As DV teams, go with your expertise, what you know, and yet raise the abstraction level of the DUT exercised in that rich and known and trusted environment.
Dave, is it okay to rephrase my comment verbally?
Yes.
So you know, I'd like that DPD solution. In my system, there's a lot that sits between the DACs and the PA itself, and a lot that sits between the PA and the ADCs that are used in that problem. That's the part I'm responsible for in my system. I want to solve that DV problem, you know, high level synthesis DV problem for that part of the design. And that's something that I'm not seeing getting addressed in the HLS flow or, you know, the system specification flow. C doesn't seem like a high enough level language for dealing with that part of it. And that's why I'm, you know, looking to Python and, you know, JSON. Yes. You know, as a way to specify the architecture of that part of the system, right? I don't even care about the registers that go into that block at the architecture definition level. That's, to me, the, you know, the registers and the bus architecture is an implementation detail, right?
Downstream,
that, you know,
yes.
that's going to get solved, and yeah, that can be done in HLS. You know, that could be done through an HLS flow. At the moment, we do something a little bit different, you know, a little bit more based on, I mean, there was a nice paper about somebody who took YAML and stuff to build the test bench. And it turns out they also build their, you know, they take the IP exact database and they implement, you know, the registers and their bus architecture and stuff like that. Right. So, you know, I'm thinking a little bit more that level of, you know, high level architecture. The data path, yeah, HLS is a flow. Somebody in my company has adopted that as the name of the output block, which I don't like, but that only covers the digital part, right?
Yes.
And that doesn't solve my problem. That's what I was hoping to see today. Otherwise, very interesting.
Thank you. Yes, in the material we talked about, starting with a floating point model as you know, again specific to the filter, to the digital block, and yes, the inputs where those models can be in a wide range of languages. Certainly, as you mentioned, Python very strong and ever increasing capabilities in the math area there, and again, there's the familiarity. So many folks today are familiar with Python, or, you know, much more familiar with that than System Verilog.
Yeah, I'm actually thinking of Python more to define the set of blocks that sit between that are, say, that number of bits in the DAC, what goes on between the baseband filter to the up converter to the driver amp that goes off chip to the PA, that comes back in, comes through some network of amplifiers, maybe filter, and then to a signal path that goes to an ADC that then finally sends data back into your DPD, right? I'm thinking of that architecture is a number of blocks, each of which could be implemented actually in C++, but how do you stitch them together, right? I don't want to describe that in C. I want to be able to describe that in a high level, how many control states do they have and stuff like that.
Mm-hmm.
Define that in Python. From Python, elaborate to C. From C, go to RTL, right? Build a virtual prototype of the system, write the software for it, hand the spec off to the analog designers, right? As we start the, synthesis of the, hand the RTL spec off to the digital team where we start working on the actual implementation. That's the flow I'm envisioning.
Yeah, for a good reason. Like the benefits that applying the best abstraction for blocks, and obviously with the goal of the highest level that you can for the benefits we've talked about. Certainly the I think there was the question earlier in terms of high-level languages for analog design, and my response was I'm not aware of commercially available capabilities there. It's very interesting, forward-looking topic in terms of specifically here talking about just system level definition as an input to your HLS. Today's talk, we obviously focused on starting with C++ design and then taking that through RTL.
Yeah, that's good, and I'm just seeing it's like, well, I can't take that to analog design, so useful to have a virtual prototype. That's the I see that as very a useful thing.
And not that you're looking for that analog model, like the analog design is still in my opinion, right, it's still black magic or black art, right? So that still has to be done or very a manual intensive process. Yet not to say that that requirements, that virtual prototype model, high level abstracts of that can't be created, shouldn't be created, and then plugged into an appropriate modeling level.
Yeah, I think there's a place for still working at the design intent level, documenting the design intent in a way that we can validate that the actual implementation implements that intent. We have a similar problem in analog with UPF. Right. Specifying the design intent as UPF, if it could be used in the verification flow of the actual analog design, rather than as in the gate level simulation flow for the analog design, that might be a more useful approach for it. But yeah, that's another place where my analog designers put all their power ports in the design and design their LDOs, and things don't necessarily follow the architecture that gets documented in the UPF architecture, right? So it gets hard to use UPF to verify, to simulate the detailed design for the analog blocks. Maybe that's not really on topic here, but it relates to intent
Mhm.
You know, capturing intent separately. If it can be made a part of the verification flow, it's more likely to happen.
Yeah, good observations. Thanks for sharing those.
I yield the balance of my time.
Where's if there's no more questions, Meili, I think we can close it down. Thanks everyone for attending, for joining, and hope to talk with you soon.